Yeah, read that.
All right. Is everyone fired up to learn about measures of scale? Yeah. And you know, this matters. This matters a lot. You know, obviously it's useful to summarize data with a position, you know, a location, and the scale. Is it this big or is it this big? You know, that's sort of it's useful. We can describe a big data set with one number or two numbers. That sounds good. But where this really comes in critically important is when we've got two different sets of numbers and we're trying to compare them. So say we've got two different means. And you know, one's here and one's here. Are they close to each other? I don't know. We have no basis for comparison. When we have information about the scale, though, you can say, well, you know, if this goes from here to here, and this goes from here to here, these numbers are far apart. These means are very different. If the scales are huge, this, you know, goes to this one, and this one belongs to one that's ever so slightly different. We say, well, you know, yeah, the means are a little bit different, but in the big scheme of things, this isn't a big difference. So we have to understand the size of our data set. How big is it along the number line before we can start asking principled questions about whether two sets of data are different or similar to one another. That seem reasonable? Everyone buy into this basic approach to statistics? So let's figure out how do we come up with a statistic for scale? So we're going to start with the mean, which is, I am reliably informed, 8. And we want to know how close to the mean are the data points. So, well, this data point is 32, 1, 2, 4. I don't know how to subtract it from 32. I think it's like 24. So we've got, you know, one distance. We've got this distance, that's 4. We've got this distance, 6, and 2 7s. Okay. So now we have a list of numbers that says how close all of my data points are to the mean. What do we do when we have a list of numbers and we want to summarize them with one number? Yeah, so we're talking about the mean. We might as well take the mean of that. Now there's one trick. And so remember that the mean is all driven by squared distances. The distance that's really important, it's a physical quantity that's actually meaningful if you're a rubber band, is the squared distance. So the way that we do this in statistics is we actually square all of these distances and then take the mean of those. So that's the mean squared distance from this center point. So let's compute that. We got 24 squared plus 7 squared plus 7 squared plus 6 squared plus 4, not 4 to 4, that's too many, 4 squared. That's 722. I think we calculated 722 before, if you remember when we were finding where the mean was. So 722 is the total squared deviation from the mean. And if we take the mean of this, if we take the average, we're just going to divide that by 5. That equals 144 point something. Good. 144.5. So what is this number the average squared deviation from the mean. Has anyone seen this number before? Shout it out if you know it.
The standard deviation.
Close.
The variance.
It's the variance. So this variance tells us something about how close all of the numbers are to the mean. It's not so useful though, because the variance is in squares. So imagine this is like inches. 1 inch, 2 inch, 4 inch, 32 inches. The mean is 8 inches. The variance is 144.5 inches squared. What does that mean? I thought square inches was for measuring something very different than you would measure with inches. So the standard deviation, we take that squared variance, what do we do with it? Square root. That equals 12, or close enough. And so the variance is often referred to, and you'll see this, I'll try not to use this kind of notation because it's not super helpful. You'll see this called sigma squared, and we take the square root of it, and we get the standard deviation sigma. That's just some notation that you'll see around. So what does that mean? That means that we can take this data set, and we can summarize it by a mean, 8, and a standard deviation, 8 plus or minus 12, more or less. 8 plus 12, 8 minus 12. So, we can summarize a group of data points. We can summarize its location and its scale. This is actually a really terrible summary. So this is terrible for a couple reasons. Number one, this 8 plus or minus 12 looks nothing like our original data set. Number two, we took 5 numbers and we summarized them with 2 numbers. This isn't a big win. So sometimes out in the world it's better just to show your original data and let the reader decide. Just plot the 5 numbers. If you have 6 mice that live for different lengths of time under a treatment regime, really often in the literature you'll see someone will plot a bar graph with the mean of 6 mice and the standard deviation. I don't like to see that. That doesn't tell me anything. It tells me 2 numbers. What I would rather see is that they had 3 mice that lived here, 1 mouse that lived a little less long, 1 that lived a little more long, and 1 that lived really long. And then maybe you could plot the mean also. So remember when I said statistics is sometimes a matter of taste? You just have to develop a taste for saying, show me the data, unless there's a good reason not to. Don't summarize data if you don't have to, and don't summarize it badly. Or at least if it is a bad summary, tell someone that this mean is very much influenced by this outlier. Because otherwise it's uninterpretable. So we've talked about the mean, we've talked about the variance. You can start to think, well, what about the equivalent of the variance if we cared about the absolute distances rather than the squared distances? We did that for the mean and we got the median. What do we get when we do that for the variance? Not much, it turns out. All of the math around statistics is built on questions about variance and standard deviation. So we're going to stick with talking about the variance and the standard deviation. For better or worse, that's how the math works out. So now we know how to summarize both the position of a set of data as well as the size of it. In this case, it didn't work very well. If you have a lot of data, the variance actually is going to, in general, give you a pretty good summary of how big, how spread out are the data. So what is the variance telling you? fundamentally, what is the variance telling you? Remember when I said that the mean gives us the position where if we strung rubber bands from all of our data points to this little peg at the mean, that would be the minimum energy position, that would be where the rubber bands would go to. So what the variance tells us is that we could move all of our data points to plus and minus that variance, and we would have the same sort of strain in the rubber bands. But if we piled 2 data points up here, 2 data points up here, and divided this one half and half on either side, the rubber bands would be stretched about the same amount. So fundamentally, that's telling us some physical quantity about how bunched up the data are. And it has a real physical meaning. It's not just, well, I'm going to square it because I feel like it. There's a good reason for that. But it is a little less intuitive than the story with the means and the variance, with the story of the means and the medians and the modes. So in the homework, you're going to practice calculating some variances. And in the second lecture, when we start dealing with large data sets, then you'll see the power of being able to calculate 2 numbers to summarize 20,000 numbers, which is a good deal. Calculating 2 numbers to summarize 5 numbers, not a good deal. Don't make plots like that. Okay, so Zach, how should we make our plots? How do we summarize a group of data with more than 2 numbers, but less than however many numbers we started out with? Dot plots aren't bad. As I showed, sometimes for a small number of data points, 2 dot plots is a better comparison than 2 bar graphs. So let me just draw out an example of what I mean. Say we've got a bar graph for condition 1 and condition 2. And we plot out the mean plus and minus the standard deviation. So what's the biology that's happening here? What's driving this effect? I don't know. Maybe the mice that were eating this chow lived a little bit longer in general. Or maybe, so it's hard to say. But if we plot the dot plot, and then we're just going to put a line for the means. And you'll just have to pretend that these means are the same. You can see that we see a very different story. Here it looks like this treatment group is on the whole maybe a little bit better. Here it's quite clear that this treatment group is on the whole, if anything, a little bit worse, except for one animal that responded really well or something else weird happened. So you should always err on the side of showing the data, except when we've got too many points that the dot plot will just be a complete mess. So what do we do when dot plots start to lose their charm? So there's a really simple generalization for dot plots that we've all heard about, which is called a histogram. So how does a histogram work? We divide our data range into a certain number of bins, and we count how many data points fall into each bin. So to make that a little more visceral, let's just divide our height range into 1, 2, 3, 4, 5, 6, 12 bins. Okay, so let's go left to right. How many go in here? 0, 0. How about this one? 1. Ooh, tricky. We've got a bunch that are right at 160. I'm going to define the bin to be inclusive on this side and exclusive on this side. Has everyone seen set notation? All right, so we count the number at the bottom of the bin, but not at the top of the bin. So how many go into this?
That changes the third bin, right?
Oh,
Because that's 155.
that's 155. Yeah, you're right. I'm just not good at drawing bin boundaries. Good eyes. All right. How about this bin?
1.
How about this one? And we could just be kind of approximate. You don't have to. 8, sure.
2.
Yeah, this one's 2. This was bad drawing on my part.
7.
All right. So this one. How about this one? 1. Okay. And then 0 is 0. So now we've taken a numbers, what was this, like 24 odd numbers, and we've turned it into 12 numbers. So that's okay, we've summarized, we've saved 12 numbers. Do we have a decent picture of what the distribution of heights are? So how do we draw out that histogram? No big mystery, of course. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Seem okay? No one has any objections from the registry? All right, so the first bin, its height, we're just going to make the height the counts, the number of elements in the bin. So this one's height is 0. What's the next one's height? 0. How about the next one? 0. Still 0. Worthless bins. How about now? 1. What next?
8.
2. 3. 7. 1. 0 and 0. Okay. So now we have a nice summary of our data. Or at least it seems like a nice summary. It seems like it's telling us what we thought we saw in the data, which was 2 different modes. And again, I'm going to call this bimodal, even though this one has 7 and that one has 8. It's not exactly correct, but it gets the shape of the data across. Now, there was a little bit of arbitrariness in this, right? What was arbitrary about what I just did?
The bins.
Right. What about the bins was arbitrary? The size of them? Was there something else that was arbitrary? The boundaries, yeah. So the size of the bins and the boundaries are 2 choices that you have to make when making a histogram. And in the homework, you're actually going to work through a histogram with a few different choices and see how that changes the histograms. So let's first talk about the sizes of the bins. If you make the bins too narrow, we basically wind up with a dot plot again, right? Like if every bin is so tiny it only sits over 1 or 2 data points, then A, we haven't really summarized our data. We've turned 24 numbers into 24 numbers. And B, we're losing the forest for the trees. In the case of a histogram, quite literally, we'll just see a bunch of trees at height 1. Okay, so what's the problem if the bins are too wide? What if we just did like 3 bins?
1 bar. You get 1 bar. Like
We get 1 bar. Or,
Well, I get to see like the distribution within that bin, if that varies.
Right. So depending on where we put the bins, we might totally lose the structure of the data. So when you're making a histogram, remember that the widths matter and the bin boundaries matter. And you should try making a histogram a few different ways to make sure it's not changing what you think the data look like. So let me give an example of how bin boundaries can be really important. Just to belabor the point. It's my favorite thing to do. so let's get a simple list of numbers. Okay. 0, 2, 4, 6, 8, 14, 16, 18. I'm pretty sure I can count by twos to 20. Let's put a dot here. 3 dots here. Dot here. 3 dots here. 2 dots there. All right. So let's make a histogram from this data where we choose relatively wide bends. So from 4 wide. All right, so let's start at 0 and go up to 4. How tall is this one? 1. How about 4 to 8? 3. Try to draw these heights right. 8 to 12? 1. And 12 to 16? 5. Okay, so from this histogram, what do our data look like? What would be the adjective that we would describe this data set as? Bimodal, yeah. All right, let's do something else completely reasonable. Let's start the bin nearest to our lowest data point rather than at 0. So we're going to go same bin width, so we're going to go from 2 to 6. How tall is that? 1, 6 to 10? 3, 10 to 14? And 14 to 18? Okay. Tell me no one's blue-green colorblind. Can you see the green lines? What does the data look like now? What does the data look like now? Unimodal. So bin boundaries matter, especially for small data sets. The more data points you have, the less the boundaries matter. The more data points you have, the less the exact widths matter. The more data points you have, the less statistics matters. So, you know, if you can, find yourself a niche where you can generate a whole ton of data, because these finer points don't matter as much. But if you are working with 6 mice, 8 mice, 12 mice, and those are all the mice you're going to get for this pilot study, you really need to fundamentally pay a lot of attention to how you present the data and how you think about the data. Okay, so right now, previously, we've only been talking about bins of even widths. Could we make a histogram with uneven bin widths? I guess you can do anything you want. Right? It's a free country. So let's exercise that freedom. Okay. I'm sure you're getting sick of number lines, but, well, they're how we plot numbers, so. All right, so let's make some data up again. Have a dot here, 2 dots here, 3 dots. Okay, so now this is about uneven bin width. So let's start with a simple bin width from 3 to 4. How tall should this be? 3. Okay, how about this one? 2 to 3. How tall should it be? 2. Okay, what if we make this bin from 0 to 2? How tall should that bin be? 2. Okay. What if we actually just did the normal histogram thing? What if it was just from 1 to 2? How tall should this bin be? 1. How tall should this bin be? 1. So clearly with even bin widths, this is totally how the histogram is supposed to look. So why should it be that when we erase this line, this goes up a unit?
The area,
What did I hear?
the area.
Yeah. Yeah. Maybe the way we should be counting these is the area, not the height. This is actually, I mean, okay, right, no one actually draws uneven bin width histograms. Well, people do, and there's good reason for it, but we're really not going to do that. But the area is telling us something fundamental about how we think about probability. And it's the ratio of the areas that matter. If you were to throw darts in the histogram, where you would hit would be proportional to the area. And so this is going to be a little more intuitive when we stop thinking about these bin heights as the total counts. You know, 3 dots, 2 dots, 1 dot. Because what does it mean for this area to be 2? And instead we're going to transform our histogram into something that doesn't care about the total number of data points that we have. So let's again draw out, you know, just some sample histogram based on data points. So, you know, we've got our bar, let's call it 4, call this bar 5, 11. Oh, I'm going to run out of room, man. 20. Call that 35. Sorry, it's in the shadow, guys. 13. 6 and 6. Okay. So that's just how tall these bars are. We have a data set and it's got this many numbers in it. What does that add up to? Was I clever and make it add up to something simple like 100? I hope so. Otherwise I wrote the numbers down wrong. Let's just pretend they add up to 100. So what if instead of making the heights of the bars, or equivalently the areas, sum to the total number of data points, what if we just make them sum to 1? So that the area of each bar is proportional to the fraction of your data set. Well, in this case, that's actually really easy, right? Like 0.04, 0.05, 0.1. So now we're starting to think about not the number of dots that we have, but the fraction of our dots. How many of our dots were bigger, or fall into this bin, or how many of our dots were bigger than a particular number? Instead of giving us the total counts, we can say, well, 20% of the dots, well, let's say 12% of the dots fall into these 2 bins. Okay, it's starting to sound like probability, maybe a little bit. And we're going to talk about this a lot more in the next lecture. How do we look at histograms and think about probabilities, not just counts of our data, but how likely is it that a data point is going to fall within a particular area? So the last thing I want to talk about in the last couple minutes of class today, what if we had a lot of bins? Like a lot of bins. We have 1 million data points. And so, we can have like 600 bins. And 1 million numbers down to 600 numbers is still totally a huge win. But 600 bins, they're going to be narrow. They're going to be right next to each other. You can't even see anything because the lines are all on top of each other. This is hard to draw. It's hard to look at. It's hard to interpret. So what do we do if we have like a lot of bins? Let's zoom in a little bit. Let's zoom in on just that area. So they're right. I'm lazy, first off. That's a lot of lines to draw. How could I draw fewer lines? Well, maybe I'll just draw a point here in the middle of each of these. And I'll just connect the points by lines. And so at least I didn't have to draw the little square caps. And maybe I'll still put the heights in. Okay, so remember we said that the bin area matters. So I've replaced, I replaced square top bins with weird, funny, pointy, jagged top bins, right? I've replaced that with that. But maybe this isn't so bad. Because, this little extra area here is probably about the same as that little corner that I cut off. So, maybe this is totally an okay way to draw the histogram with fewer lines. So, now we're going to draw our histogram like this. And then, there's still lots of lines here. Okay, since I'm even lazier, I'm just going to not draw these lines. Okay. I think we accidentally did calculus again. Does everyone remember from high school calculus about how if you have a lot of thin bars stacked up next to each other? So if each of these heights, if each of the areas is proportional to the total fraction of the data that fall within that bin, what is the total height? Total area?
1.
1. Okay, so what does that mean for this curve? What's the area under this curve?
1.
1. It integrates to 1. And what does the area of any arbitrary slice tell us?
The probability of getting something within that range.
That's correct. So this is known as a probability distribution. The total area under the curve is 1, and within any slice gives us the fraction of the data that are in that slice. Anything that has those properties, anything that integrates to 1 and doesn't go below 0 is a probability distribution. We're not going to be doing a lot of math, and we're certainly not going to be doing much more calculus about probabilities and distributions. But it's important to know that the histogram generalizes perfectly over to this probability distribution. You're really thinking about the same things when you're talking about the areas within the histogram bins versus the areas of some arbitrary slice of a distribution. So that's how we get from very intuitive statistics, counting up numbers, calculating the means, drawing out a histogram, to actually thinking about the fundamental probability distribution. How likely are different events in different parts of the number line? And with that, I think I'm going to wrap up the class a little bit early. I want to remind you the homework is now live on the Blackboard site. You can download it. You'll have to figure out where you downloaded it to, navigate to that directory from within the IPython notebook, and the Lecture Zero PDF will give you instructions about how to get that set up, how to do that navigation. Load up the notebook, start running it, and start working your way through. There are interactive problems where you type in the answers into little gray boxes. You can keep running the code as often as you want until you get the answer. It'll give you explicit instructions about how to do that. If any of this is confusing, if it doesn't work right on your computer, post a note to the Blackboard, come to the Thursday session, we'll get you sorted out. As far as homework policy, feel free to work on this with other people. These aren't group assignments, don't hand them in as groups, fill them out yourselves, but don't feel like you can't ask someone for help. The important thing is that you learn how to use these tools. So if you're cheating, you're cheating yourself. It's a 1-unit course. This is for you guys to learn your best. So let us know if anything's not working with one. Mike, do you have anything you want to add?